In this video, we're going to take a look at a concept called linear approximation. So the idea of this is that you have some graph. So this red graph representing some function y equals f of x. What we're going to do is we're going to linearize that function so that around a point, so that if I wanted to know the value of the function at some x coordinate close to this point, instead of using the actual function to find that y coordinate, I could use this line, and that would give me a very similar approximation there to what that y value is. And so we have this equation to give us the linear approximation, and it is that the linear approximation f of x would be f of a plus f prime of a times x minus a. Now, where does that come from? Is point slope form, right? So if we think about point slope form of a line, y minus y1 equals m times x minus x1. Instead of the point being x1, y1, okay, and we're talking about this point right here, instead of x1, y1, we're looking at a f of a, right? So if I just think that, well, if it's y minus f of a equals m times x minus a, if I add that f of a over, then I get y equals f of a, I'm going to put it in front, plus m times x minus a. And we're almost there. The only thing now is the slope, which we should know at this point that if I do the derivative and I plug in that a coordinate, that gives me the slope of the tangent line there, right? So that m gets replaced with f prime of a. It's the derivative evaluated at that point, and that would give me my slope. And so this is just the equation of a line, and it is basically the line that is it is the line that is tangent to that point, so that we can use that to approximate some other y values of our curve. Okay, so I'm going to jump into an example and how we can use this. So the question is, we want to find the linearization function to the function f of x equals the square root of x plus 3 at a equals 1. And then I'm going to use that to do a couple of approximations. Okay, so the first thing I want to do is I'm going to think about the linear approximation. And since we're already calling our original function f, I'm going to call the linear function g, just so that I have a different thing in mind there. So g of x, my linear function that I'm going to make for this, it's an approximation, is going to equal f of a plus f prime of a times x minus a. Now again, a is 1, and my function f is the square root of x plus 3. So what do I need to figure out? I've got to find a couple of things here. I have to figure out what f of a is, and I have to figure out what f prime of a is, which means I need to figure out what f prime of x is, and then I can plug in a. So f of a is easy. That's just plug in 1 into your original function, so I would get the square root of 4, which would be 2. F prime of a, if I think about doing the derivative of this, this is x plus 3 to the 1/2 power. So the derivative there is going to be 1/2 x plus 3 to the negative 1/2 power. But then I'm going to evaluate that at 1 because a is 1. So that's going to be 1/2 1 plus 3 to the negative 1/2 power, which if you evaluate that, that's going to be 4. The square root of 4 is 2 to the negative first would be 1/2. I get a half times a half, which would be 1/4. That is f prime of a, f prime of 1. So our linearization function then is going to be that g of x is equal to f of a is 2, f prime of a is 1/4, that's my slope, times x minus a, which would be x minus 1. And this is our linearization function. So again, the idea is if I want to evaluate this function, my original function f of x, at some x value really close to a, then instead of plugging it into f, I can plug it into g. So the next part of this asks us to use this function to approximate the square root of 3.98 and the square root of 4.05. Well, if I want to evaluate the square root of 3.98, what does that mean I wanted to plug into f? Right? So if I want to approximate 3.98, square root of that, that means that x was 0.98, right? 0.98 plus 3. 0.98 is close to 1. So this linear function ought to give me a pretty close approximation for that. So I want to evaluate f of 0.98, which would be the square root of 0.98 plus 3, right? That's what I want, and I want to figure out, well, what is that value? So the idea is, instead of plugging 0.98 into f, I'm going to plug 0.98 into g. And now I can use a linear function instead of a square root function to do this. And I would get 0.98 minus 1. And I'm gonna work through that a little bit. That's going to give us 2 plus 1/4 of 0.98 minus 1 would be negative 0.02, or I'm going to call it negative 2/100ths. And I'm going to keep evaluating this as a fraction here. So that's going to be 2 plus, that's going to be negative 1/200ths. If I multiply that by a fourth, just canceling here, that's a 2, that's a 1, and multiply across there. And so that's going to be 2 plus negative 1/200ths. 2 is 400/200ths, so that's going to be 399 200ths, which we'll find the value of in just a second here. But the idea is, instead of doing that, like, I can actually work through that math, and it's just solving a linear function, as opposed to trying to do that square root by hand, right? That's not something that we could do. We could do this and get a very close approximation. So I'm going to go to Desmos really quick and look at this. So the original function was f of x equals the square root of x plus 3. A was 1, so we had the 0.12. And then our function g of x is 2 plus 1/4 of x minus 1, which gives us this function that's going to be the linearization function for that graph. And what we wanted to say was, instead of finding f of 0.98, so that would be the square root of 3.98, which is 1.9949. Instead of doing that, I'm going to do g of 0.98 and see how it is a very close approximation to what f of 0.98 was. So that's the answer that we get there, 1.995. Okay. The very next question there is asking us to estimate the square root of 4.05. So in that case, what is x? What plus 3 gives me 4.05? So that's 1.05, again, close to a. It's close to 1. So in this case, the actual value, if I were to do f of 1.05, I would get this. If I use my linearization function instead, and I worked through that, I would get something that is very close to what the actual value is there. So again, you are finding a linear function that if you plug in an x value close to the a value, it will give you an answer that is close to what the actual y value is.